morning. Now that we know how to estimate the value of the heat release from a given explosive and also how to calculate the rate of heat release from the explosive, it is time we think in terms of a simple theory. A simple theory, what I mean is something by which we make some assumptions and a simple theory to interpret, let us say, a theory of an explosion. We will build upon the theory as we go along, but to recapitulate what we have done so far, we calculated the heat of a reaction, and let us be very sure, because there are certain things which I still want to add on. Supposing we have a chemical reaction between, let us say, a fuel A and let us say an oxidizer B, and in this reaction we have A moles of A, that is the fuel A, and small b moles of the oxidizer B, and it forms, let us say, C moles of product of capital C, this is the product, and I have something like D moles of, let us say, another product D. Then what did we tell? Well, the heat of the reaction is equal to minus of the heat of formation of the products. That means we have per mole of C, the heat of formation, standard heat of formation is delta heat of formation at standard conditions into C moles, that is the total for these C moles here, plus I have D moles, I have heat of formation at standard conditions for D over here, this was for C over here, this was for the products over here, and I have minus the heat of formation of the reactants, which is equal to A into heat of formation under standard conditions for A plus B moles over here into heat of formation under standard conditions for B over here. Therefore, we got the heat of reaction and we say, well, I have A moles, I can refer heat of reaction per mole of fuel or heat of reaction for the total A plus B moles of the mixture, I can calculate this particular value, and this is so much in kilojoules for the reaction. I can also convert it to kilojoules per mole, which we used to interpret the rate of a reaction. Now, one thing you would have noted that I am talking of the products at standard condition. We are also talking of the reactants at the standard conditions, mind you, 25 degrees and 1 atmosphere pressure. If it is a gas, if it is a liquid or a solid, at 25 degrees centigrade alone. Now, the question comes, well, the reactant could be at a different condition, maybe in a very cold climate. Well, the reactant could be at 0 degrees centigrade or could be at even minus 50 degrees centigrade under different conditions. Well, the reactants need not always be a gas like at 25 degrees, it could also be a liquid, like you could have a liquid hydrogen reacting with liquid oxygen. Therefore, how do we get, maybe if the reactants are not at the standard condition like what is specified here, how do you interpret or how do you calculate the heat of a reaction? Well, it is possible to say, well, this particular heat of reaction is when the reactants are at the standard condition. Therefore, if I can supply some heat, maybe if the reactants are at temperature much lower than the standard condition, I supply some heat maybe to bring, that is, I have sensible heat to bring the reactants to, let us say, 25 degrees centigrade. And in case I have something like liquid methane, whereas methane is taken as a gas, I also supply the latent heat to at the boiling point and then bring it to 25 degrees. That means I supply the sensible heat and latent heat to bring the reactants to 25 degrees centigrade, then I can use this. Therefore, what really happens is, well, part of the heat of reaction minus the sensible heat and the latent heat to bring it to standard condition plus, let us say, latent heat to bring it to standard condition now becomes the heat of the reaction. I think, therefore, this is one way I can still do the problem. If it is at a temperature lower than the standard, well, I subtract it. If it is higher than this, let us say it is at 40 degrees centigrade, a very warm climate, or 50 degrees centigrade, what happens is some excess heat more than what is available at standard condition is existing, and therefore, in this case what happens is, when the temperature is greater than 25 degrees centigrade, that is standard condition, the heat of reaction is equal to the heat under the standard condition plus I have the value of the sensible heat over and above 25 degrees centigrade, and if it is something which still corresponds to something else like some other state, maybe I have to take care of the latent heat which is associated. Therefore, in this way I can calculate the energy liberated from a reaction at any condition whatsoever. Therefore, we have talked of temperature, we talked of atmospheric pressure, but I may again ask myself another question: what if the pressure, we say it is calculated under atmospheric pressure, which is standard, and the pressure at which we do is 1 atmosphere pressure. What if I have an explosive mixture which is contained in a gas and the initial pressure of the reactants is, let us say, 250 atmospheres? How do I calculate the value? Well, for 250 atmospheres, maybe I have to be a little careful because my equation of state may not be ideal, but in case the equation of state is ideal, I am talking of 10 atmospheres or 5 atmospheres or so, I tell myself, well, as per thermodynamics, the heat of the enthalpy is only a function of temperature for an ideal gas. Therefore, pressure will not really influence it, and therefore, the heat of formation, what we are calculating is only a function of temperature, and therefore, pressure will not affect your calculations. But we must also remember, when I increase the pressure, I am talking of PV is equal to nRT, and therefore, the moles are directly proportional to the pressure. Anyway, the moles A, B, what I am talking over here, A moles of A and B moles of B are anyway taken care of, and therefore, I can continue to use the same expressions for calculating at different pressures. Therefore, we can calculate the energy liberated from an explosive under different conditions of pressure, maybe different conditions of temperature, and this is how we proceed. With this background of heat release, when we talked of the rate of chemical reaction in the last class, what did we tell? Well, I tell that maybe the heat release from chemical reaction, we call it as Q, chemical reaction dot, and what is the unit? You have kilojoules per second, and what was it equal to? The rate of the chemical reaction, and what was the rate of a chemical reactions in moles per cc into second into the volume, let us say in cc, it becomes moles per second, that is this. If I multiply by the heat release Q in so much kilojoule per mole, we got the heat release in kilojoules per second. What happened? Mole and mole got cancelled, cc got cancelled, I have kilojoules per second, which is the rate of heat release. We also had the expression for omega, and we said, well, omega is a combination of the reaction rate constant and the Arrhenius law, and we were able to write Qc dot as equal to A into the concentration. We just said any general concentration. We said, well, if it is a first order or a simple reaction, it is just C. If it is product of fuel and oxidizer, it could be C squared ACN into exponential of minus activation energy divided by the universal gas constant into temperature. Well, activation energy we said was large, it has units of joules per mole, this is joules per mole, Kelvin is the universal gas constant, this is Kelvin, into I have V into Q. We said, well, this is the amount of heat liberated in kilojoules per second. See, we also wanted to get some idea on how the heat release varies with time. We told ourselves, well, if I have initial concentration C naught of the reactants, I just consider one, let us say Ca or something, initial concentrated in C0, and by the time, let us say with respect to time, when the reaction gets completed, well, the concentration of the reactant becomes 0 because only products are there. Therefore, maybe C naught gets consumed in this particular way with respect to time. That means when the reaction is completed, I have all products and you have C naught going to 0. Well, if I were to look at temperature, well, the temperature initially was ambient with respect to time, and what happened? We are plotting temperature with respect to time. Initially, let us say 25 degrees centigrade is the temperature. Finally, well, everything is burnt, I get the maximum temperature, and therefore, we said, well, the rate of a reaction goes like this. This is the way that temperature varies. And we were able to put C, the concentration, at any time. That means when the temperature is T, I tell myself when the temperature is T, well, the concentration could be C. we put C in terms of maximum temperature and the initial temperature T naught, and we got an expression. Well, let us put that down because that will help us to be very clear about what we were doing. We got A into the concentration, initial concentration to the power n. We also got the expression T maximum, that is maximum value over here, minus the temperature at any point in time into Tm minus T naught to the power n again, and I carry the other expressions through, namely V and Q, so much kilojoules per second. We learned how to plot this and we interpreted how the energy will release, and we said, well, in this what is missing? I said C is given by this, V and Q, well, I have to take this into account, therefore, I still have the exponential term, and this is what really makes the system interesting, because let's now take a look at it. R naught into T over here, so much kilojoules per second. And we said, normally whenever we talk in terms of explosives and chemical reactions in explosives, the value of activation energy is large, and when the activation of energy of a chemical reaction is large, what did we tell ourselves? Well, if I plot Q dot C, now as a function of time or equivalently, since as time increases the temperature increases, or equivalently as a function of temperature, either one on the x axis, what is going to happen? Well, I have something like a reaction starts here, goes to the maximum, comes back over here, and this is where we say, well, this is the total, the area under this curve with respect to time is the total heat of the reaction. Well, the Q dot in terms of kg per second is like this. That means for some time when the temperature is low, the reaction rate is slow, and then all of a sudden it shoots up your maximum, and once the concentration is essentially completed, well, the reaction rate comes down and it comes down to 0 at the final state. Now, if I put different values of exponential that is EA, that is the activation energy, what is it I get? If my activation energy increases, then the effect of this particular term is to push it still lower. Maybe it comes down over here and it peaks over here, and then it comes down over here. In other words, the effect of increasing the activation energy is to decrease the effective time of chemical reaction, that is the duration of the effective heat release comes down, and this is what happens when the activation energy is large. If I have the activation energy to be very small, what happens? Well, the energy could be released something like this, because the moment, because it has to overcome a very small barrier, the activation energy is small, and this is, let us say, EA small. With this background, see, we are only interested in large values. I am not interested in the yellow line for which, like we say, phosphorus immediately burns. I am not interested. I am interested in explosives. Therefore, we will address the situation for EA to be large. That means we will be concentrating maybe in this particular zone for which EA is a large number. Therefore, let's now get going. Let's now say, well, I have an explosive. I have certain volume of explosive over here, some volume. Well, it contains, let us say, some moles of the substance and whose initial concentration is, let us say, C naught. Well, the ambient, that means I have a boundary. The boundary could be a physical boundary, or let us say some boundary over here. Let us say that the area of the boundary is S meter square. The volume is, let us say, VCC or V meter square. This is the initial concentration. Let the ambient temperature be T ambient. Let the initial temperature of this explosive be T naught. Now, we tell ourselves, if let us say T naught is less than the T ambient, what should happen? If T naught is less than T ambient, well, the temperature, that is the heat, will flow in this direction, because here the temperature is higher, here the temperature is lower, the heat will flow and heat up the explosive. That means, and how do you estimate the heat transfer? Let's put down an expression. We tell that the heat transfer, and let's put the same thing, the rate of heat transfer. We say Q dot H is equal to, it depends on the temperature difference. We have T ambient minus T naught, and what drives it? It is the heat transfer coefficient into surface area, we say so much kilojoules per second is the heat transfer over here. Therefore, if I were to plot this particular figure, what is it I get? Well, I have the temperature here, I have the ambient temperature is T ambient over here, and what is going to happen? Well, the ambient temperature is higher, and therefore, if I were to plot Q dot H over here, I have, well, the temperature is lower, maybe the line is somewhere over here. That means heat is flowing. This is my volume of the explosive, heat is flowing from ambient to the lower temperature here. And when heat flows over here, this temperature rises. Let us say if this temperature T naught by chance happens to be higher than T ambient, what is going to happen? Well, I am plotting now with respect to T naught over here, that is T naught over here, this is the value of ambient. If T naught is there, well, I have a positive heat transfer, and therefore, I say, well, Q dot H is equal to heat transfer coefficient into surface area into T minus T ambient, where T could be the temperature at any instant of time. Maybe the temperature keeps increasing, and as temperature keeps increasing, the heat transfer increases, just like we had the figure of due to chemical reactions, the temperature is increasing. As the temperature increases in this particular volume, the heat transfer increases, and therefore, the heat transfer is given by this particular curve over here, which we see is linear from this particular relation. And the slope here, the slope is given by, you say Q dot, therefore, the slope is given by the product of H into S is the slope of this particular line. Therefore, let us now examine this in the context of the heat release. In the heat transfer, I am sorry, it should have been in the context of heat transfer and in the context of heat release. Let us examine these two and try to build up a simple theory for being able to interpret the explosions. Therefore, let's get started with this. We have to make some more assumptions to be able to keep going. One thing we can assume to begin with, maybe we have to relax it as time goes along. Let us say within this volume of the explosive what we are considering, let us assume that the thermal conductivity of this particular material of explosive, whether it is a gas, whether it is a solid, whether it is a liquid, the thermal conductivity is very, very large, such that all points have the same temperature. Let us also assume that the diffusivity is so large that the concentration at all places is the same. That means, we are assuming a point here and a point here has identical temperature, identical concentration, or rather a particular point in this particular volume is representative of the total volume, and this assumption of infinitely large thermal conductivity and infinitely large diffusivity says, well, I can represent the entire volume through one particular property, and such an assumption is known as lumped mass system or lumped mass assumption. That means, we tell ourselves whatever we do, if there is a change in temperature, well, it affects throughout the volume. It is not that the temperature gets affected here, the temperature is not getting affected here. We also say the concentration is changing throughout the volume at any time t, well, it is a uniform property. With this assumption, I can tell myself, if I were to plot the value, let us plot the value of heat release, then look at it with respect to heat release due to combustion. The way we say, well, chemical reactions are taking place. Let us take a look at the initial phase of it, wherein the curve went like this. Let us plot it with respect to temperature over here, which we have done just now. We tell ourselves the value, this curve depends on, if I look at this particular expression, well, it is going to depend on the initial concentration, well, it is going to depend on the volume, it is also going to depend on the value of the heat release per mole. Therefore, this for a given value of C naught, for a given value of V, and for a given value of Q, well, this is the curve. If I increase either C naught, V naught or Q, what is going to happen? Well, the curve will go up. I can have a series of curves, and all these, the increases in as you increase C naught, as you increase V naught, or as you increase Q naught, either of them, the curve will keep going up, and this is how the characteristics of the heat release will take place. Now, this is how the heat release takes place in a reaction. this is how the heat transfer takes place, and let us consider the case wherein the temperature here is greater than the ambient, and let us put both of them together and try to see whether we can interpret it or make some sense of it in some way. Well, now I tell, well, I make a plot of, let us say, Q as a function of temperature, let us say Q dot, and this Q dot could either be QC dot and QH, that is the heat transfer. I want to say this, let us for the present assume that the ambient is at a temperature T ambient, and therefore, I tell myself, well, I can plot the heat transfer relation, that is QH, as function of temperature to be given by this particular line over here. This particular line tells me the value of Q dot H for a given value, and the slope is equal to, we said, is equal to the heat transfer coefficient into the surface area, that is H into S over here. Now, I could have different values of heat release. I want to put it in the same curve. I could have, if my concentration, that is the initial concentration or the value of capital Q is such that I could get a value of QH over here, Q dot C over here, the heat release from chemical reactions. I could also think in terms of a heat release which is such that I get a curve over here, Q dot C, that is maybe I increase the value of concentration, I say this is equal to 2, this is equal to 1 over here. And what are these two curves with respect to this? Maybe for a particular value of the surface area for a given volume, maybe by changing the initial concentration or the exothermicity Q kilojoule per mole, I can get my heat release to be here or here. What does it mean if the heat release is here and my heat transfer is over here? Heat transfer, as we told is, this is the volume, heat is getting transferred out. We said the heat transfer is equal to Q dot H over here, and what do we find? That the heat loss from this particular volume, which is V over here, concentration is, let us say, C naught, and the exothermicity is Q, is higher than the value of energy release due to the chemical reactions which are taking place. And therefore, what is going to happen? Since over the range of temperatures of interest, the energy released by chemical reactions is less than the heat which is transferred out. That means the loss is more, whereas the heat which is getting generated is less, and therefore, what is going to happen? The temperature is going to fall further, and therefore, what is going to happen? This particular volume which contains the gas can never really progress in temperature. That means, the temperature can never really increase, temperature with respect to time can never really increase, and it just keeps falling, and therefore, this particular volume of the explosive cannot really explode. This corresponds to the condition which we talked of. You will recall, we said, supposing I have an explosive gas mixture like hydrogen and oxygen mixed together, if the heat transfer from this is such that the rate of reactions at low temperature is so small, that means so small compared to the larger value of heat transfer, well, this volume is always stable, it never reacts, and therefore, we say this corresponds to the case wherein no further increase in temperature is possible. Let us take a look at this. Supposing the initial concentration is such that now what is happening, the heat release is always greater than the heat loss, and therefore, the temperature of this particular volume in which heat is getting generated is excessive of the heat loss, that is QH taking place. Therefore, the temperature keeps on increasing. When temperature increases, heat loss, the heat generation rate is further increased, and therefore, it goes into the cycle of heat generation being always greater than this, and therefore, it just explodes. That means, this corresponds to an explosion, because the heat generation is progressively increasing and it is always greater than the heat loss. Now, under critical conditions, under some conditions, I can also think in terms of, let us put it in a slightly different color. Under different conditions, I can always think, well, I can think in terms of a concentration of heat release such that I can get a curve like this. And in this curve, we see, well, I have the heat loss curve which is QH, which is by heat transfer. I have a critical value of maybe V or Q such that now it intersects this curve at 2 points, let us say A and at some particular point B. Therefore, we say, well, one case is, well, no possibility of an increase in temperature. Well, the heat generation rate is so high, higher than the heat loss rate, that it just goes into a cycle of reactions and explodes because the heat release is excessive. This volume keeps on increasing in temperature and such that there is an intensified chemical reaction. But in general, I can say, well, it is also possible for given values of heat release that it can cut the heat transfer curve at 2 points, maybe point A and point B. Let us examine what are these 2 points like. Do they represent something which is meaningful, by which I can interpret this in some way I can interpret these points? Let us start with point A. At point A we find this, I have a zone to the left of this point, this is this particular zone over here, maybe over here in this particular zone. In this particular zone, if I take any point, that means I am talking of a point, I have a temperature T A over here corresponding to point A over here, and in this zone, well, if I take any temperature over here, I find that the heat release is greater than the heat loss, that is the heat transfer out of the volume, and therefore, the temperature will build up and therefore, at the next point it will come over here. I find still the heat generation by chemical reaction is higher than heat loss, therefore, the temperature comes up and it will reach this particular point. Therefore, we say to the left of point A, if by chance I have the mixture at these temperatures, well, the point always goes in this particular direction and reaches point A. How about to the right side of point A? If I look at the right side of point A, what is it I get? Well, over here on the right side, if I say, well, I choose a temperature over here, the temperature T is higher than T A, well, the heat loss is higher than the heat generation rate, and therefore, what is going to happen? The temperature will fall, it comes over here, well, it is still higher, it comes over here, and therefore, even on the right hand side, the heat loss rate pushes the point over here. Therefore, in this region to the right, as long as this point does not exceed this particular point, what happens is the point gets pushed over here and the point is always reached over here. Therefore, it is a stable point. What do you mean by stable? Any perturbation, any change about this point always leads it back to this particular point, and we say, well, the point A is stable. And when I say point A is stable, we say, well, a temperature T A is such that the explosive, the given volume cannot explode, because it is always going to be at the same temperature. And this is what really happened. If I consider a mixture of gases in a given volume, such as hydrogen and oxygen at room temperature, whatever you do, it does not really change its initial temperature. It cannot go to higher and higher temperatures, and therefore, we say, well, it is a stable temperature. Let us similarly go back and see what happens at the point B over here. Let us again say, well, this is my temperature here, this is my temperature axis over here, this is point T B over here. Let us again go back to the left of point B, and what is going to happen to the left of point B? Well, I take a point over here. If I take a point over here, I find heat loss is greater than the heat gain, which is shown by the purple line, and therefore, it comes over here, it comes back to A over here. Therefore, any point to the left of point B always comes back to the stable point. But if I were to take a point to the right of point B, what is going to happen? To the right of point B, well, the heat release rate, that is Q dot C over here, is higher than the heat transfer rate shown by the green line over here, and therefore, I will get a higher temperature. Therefore, the temperature goes up, I have more chemical reactions, and therefore, what is going to happen? The temperature over here will keep on shifting to the right, and therefore, I have more and more heat release, as is shown by the violet line over here, and ultimately the given volume increases in temperature. As temperature increases, more heat is generated, or the reaction rate is faster, and ultimately the volume explodes. And therefore, we say, well, point B will correspond to what we technically call as the ignition point or the ignition temperature. Let me write it down here. Therefore, T B is a point at which if I can increase the temperature of this lumped volume beyond point B, well, the substance ignites, keeps on reacting, and it generates higher temperature and higher rate of chemical reaction, and we call Tb as the ignition temperature. Therefore, to be able to ignite any mixture, what is it I have to do? I am at the ambient temperature, let us say T ambient. I have to increase the temperature to the level of Tb. That means, I have to supply some energy from the ambient condition to Tb, and the amount of energy supplied over here is what we call as the minimum ignition energy, or simply we can say so much is the ignition energy. Therefore, now we say, well, the simple thing of relating in a given volume in which all the properties are lumped, we tell ourselves is able to tell us what do we mean by ignition. We know we have to go back beyond point B, which we can say, just like we say it is a stable point, we say B is unstable point, and the unstable point corresponds to ignition, because anything to the right causes the chemical reactions to go faster, and therefore, we say I have to supply a minimum ignition energy of to increase my temperature to a level beyond Tb, and therefore, this is my ignition energy. Therefore, on this curve of different heat release versus a given value of heat loss, we are able to see this point, namely point A, which is stable, point B, which is unstable, or the ignition condition. Let us go one step further and see whether we can interpret it in a slightly different way, because we said, well, in the given volume, I could have something like let us say different values of heat release corresponding to different values of concentration. But similarly, I can also talk in terms of, let us say I have a given volume, and let us say this given volume has a given value of, let us say Qc dot, that is the heat release value, so much kilojoules per second, which is given by a particular curve over here. This is the value of Qc. I want to put on this same curve, well, I say instead of plotting just Qc over here, I plot Q dot in general, and therefore, now I plot the value of QH. Now, I could have an ambient temperature which is very high, let us say this is my temperature axis, this is my Q dot axis. Well, I say I have my ambient temperature to be a high value, T ambient is high, and for a given value of the heat transfer coefficient, for a given value of surface area, well, my heat loss curve could be, let us say the heat loss curve is over here. This is my slope, the slope is equal to proportional to Hs over here. This is my value of Q dot L, or Q dot heat transfer, Q dot loss from the given volume. This is my value of Q dot C over here. If by chance, let us say, well, I say no, my ambient temperature is very low. Let us say my ambient temperature is over here, it is let us say minus, it is 0 degrees, it is like minus 20 degrees. And therefore, what is it I get? For different values of temperature, my slope is the same, therefore, now I get another curve which is over here. In other words, this is my second curve here, which I say is Q dot H, this I say is Q dot 1 H1, this is Q dot H2, and therefore, I tell myself if my heat loss is of this value, well, my heat generation curve is always much above my heat loss curve, and therefore, the substance will go into further reactions, that means there will be an explosion. But if my ambient temperature is so low that my heat transfer is very much higher than my heat generation rate, well, the explosion cannot take place. I could also think, just like I thought over here of point A and B, I could have ambient temperature T ambient over here, which gives me point A which is stable, point B which is unstable. Therefore, we are able to relate the conditions under which an explosion would occur, maybe by relating from a given volume what is the rate at which heat is getting transferred out and what is the rate at which heat is getting built up into the in a given volume. This is, we say, the energy rate of energy release within the volume, and this is the rate at which energy is getting dissipated away from the volume. Therefore, we talk of the ignition temperature unstable point, we talk in terms of a stable point. Well, this is all about the theory of a simple theory, but let us not forget that whenever we talk of this, we are talking in terms of a lumped mass system, that is the temperature and concentration at any point within the volume remains the same. That means a point temperature, a point in concentration is representative of the whole volume. Now, let us see whether I can interpret something more in this. What if my heat transfer line is somewhat tangential to this? Let's take a look at this. We tell ourselves, well, I'm interested in a condition wherein my QC could be a tangent to this particular curve. That means it does not intersect at 2 points, and what is happening is, well, I have a curve like this. It is tangent at a point, let us say C over here. Or coming back to this particular curve, I tell myself, can I have a curve in heat release? Let me put that curve in white color chalk. Can I have a curve in heat release such that it is tangent over here at the point C? What is this condition of tangency which I am talking of? That means I do not get a stable point at all. Well, I also am not getting the unstable or ignition temperature. What is this particular point over here? Let us try to interpret this. Well, to the left of C, well, the heat generation is always higher than the heat loss given by the green line, and therefore, what is going to happen is any point is going to come back over here. Therefore, it is something like a stable point. But to the right of this particular point, the heat generation is always greater than the heat loss, and therefore, the point shifts over here, temperature increases and you have an explosion. That means this particular point is something like an unstable point, but it is the minimum temperature at which maybe some ignition is possible, and this particular point C, that is Tc, is known as the critical temperature. People also call it as the auto ignition temperature. That means, if I can increase the temperature to a value Tc, well, the substance automatically goes into this thing. And what is the difference between auto ignition temperature and ignition temperature? Well, the ignition temperature is higher because I have to supply energy such that I go to this, whereas in this case that is the minimum value of energy required to auto ignite a particular mixture. Therefore, maybe I would like to find out what is the value of the auto ignition temperature, and if I say, well, this is the point over here which corresponds to T ambient, the temperature increase from T ambient to Tc is what we have to heat the mixture, and this temperature increase Tc minus T ambient is what we call as the preheat. Well, these are the temperatures which these are the few temperatures we must remember. I could have a stable temperature A, I could have an unstable temperature B, I could have the auto ignition or the critical temperature Tc. The difference between Tc and T ambient corresponding to the same heat loss line is what we call as the preheat temperature. Right? Having done these few things, namely we are able to interpret something, let us try to see whether I can get an expression for Tc. And for that, let us put down what is the expression at A, what is the expression at B, and whether I can really derive an expression for Tc and get the value of Tc minus T ambient, and this is what I do in the next 5 minutes. Therefore, let's do this exercise. We tell ourselves maybe at point A, at point B, at point C, what is the commonality at A, B and C, or we have at A, B and C over here? Well, in these cases both the heat generation rate QC dot is equal to QH dot 0.1, and therefore, what is it I get? We said QC, we have the expression available, we have A into exponential minus EA by RT, R naught T, into we get the value of Q, we have the value of V, that means A exponential minus EA, we forgot the value of initial concentration to the power n. This is the heat release by chemical reactions. And what is the value of heat which is getting lost from the system, which is equal to heat transfer coefficient into the surface area. Heat transfer coefficient is equal to maybe watts or joules per second, meter square degree Kelvin or degree centigrade. This is meter square over here into I get T temperature of the volume minus the ambient temperature over here. This is true for point A, B and C at which the equality is mentioned is obtained. Now, for the particular case of critical temperature, can I think in terms of any additional condition? See, this is true at point A, B, C. What is so specific to Q, specific to the condition at point C, maybe at point C over here? What is it I observe? I observe that the heat transfer line or the heat loss line is tangential to the heat generation line. That means, I have my x axis is temperature and therefore, I can tell myself d by dt of the value of heat release rate QC over here is equal to d by dt of the value of the heat loss rate, and therefore, I can say at the critical condition of corresponding to Tc or the point C as it were, what is it I get? D by dt of Q dot C at the condition at the point, let us say C, is equal to d by dt of Q dot H at the point C. That means, let us say at the point C, maybe at the point C over here, and therefore, what all I have to do is maybe yes, I can differentiate this with respect to temperature, I can differentiate it with respect to temperature, and what is the expression I get? Let us write out the expression. Well, I start with the right hand side. If I differentiate this term, I get Hs into H is a heat transfer coefficient constant, surface area is constant, d by dt is 1 over here, well ambient temperature is a constant, this is the value of d by dt of Q dot H at the point C, and similarly if I were to differentiate this, I get A into exponential of minus EA by R naught into T square, because R naught T as it is, this is within this particular term, and now I have to differentiate this expression, it is equal to minus of EA by R naught into T square, this is the value, but minus EA came over here, 1 over T is minus 1 over T squared, therefore, this is positive over here, and what are the other terms I get? Well, I have Q into V into C naught to the power n, and this is at the condition T is equal to Tc, or I get Tc over here at the point C. Similarly, I have this expression at point C, therefore, it should be Tc at the point C, it should be Tc at the point, it should be Tc, and therefore, if I were to write the equation for heat being, that is the heat transfer being same as the heat generation term, I have into Tc, that means T becomes Tc minus T ambient is equal to A into exponential of minus EA by R naught into Tc into I get the value of Q, I get this expression QV into C naught n. Well, this becomes my gradient equation 1, this becomes my equality in the heat release rates. And now, see, I am interested in the value of the critical temperature Tc. If I were to divide one by the other, let us say I take equation 1 divided by equation 2, what is it I get? On the left hand side, I get 1 over Tc minus T ambient, and similarly, I take equation 1 and divide it by this particular equation, I get the value as equal to, well, A and A gets cancelled, the same exponential term gets cancelled, well, the Q, V, C naught n gets cancelled, and what I get is I have the value of EA by R naught into Tc squared. Or rather, this equation, if I were to simplify, tells me, well, I have Tc square, I bring it on this side, and now I take Tc square is equal to EA by R naught into, I get Tc minus T ambient, or rather what is it I get? I get Tc square minus EA by R naught into Tc. Now, I bring this also on the left hand side, I get EA by R naught into T ambient is equal to 0. Well, this becomes my final equation. I am interested in Tc. I find well T ambient is fixed because for a given ambient I am doing this problem. And what is it I get? I find I have an equation in T c which is a quadratic equation. I want to solve for T c and let us solve this. Let us see what number we get. Therefore, I solve this quadratic equation in T c and what is it I obtain? I get T c equal to minus middle number, that is E a by R naught into plus or minus under root of middle number squared E a by R naught squared. Then I find it is minus 4 into the first into the last number. I get 4 into the first number is 1, the last number is E a by R naught into T ambient is the last number divided by 2 into the first number, or rather this gives me the value as E a activation energy divided by 2 R naught plus minus, let me take E a by 2 R naught outside again, E a by 2 R naught again outside into I have the under root over here, and since I have taken this outside I have 1 plus now I have taken this outside, therefore I should get 4 into I get R naught divided by E a into T ambient over here, and this becomes my value of T c. Now I find yes, being quadratic I get 2 roots. Let us examine the roots of this equation. One thing we must not forget, the activation energy we said is extremely large, and we also said well the activation energy varies between let us say 80,000 joules per mole to something like 160,000 or higher joules per mole. Whereas the value of R naught universal gas constant is something like 8.314 joules per mole Kelvin. Therefore, we find well E a is extremely large number compared to R naught, and therefore, if I have the plus sign over here, what is going to happen? I add 2 large numbers, I come back with numbers T c of the order of something like 50,000, 100,000 Kelvin, which is fictitious, and therefore, I tell myself well the number positive sign is not possible. And therefore, on these physical grounds such that I cannot have such high temperatures which are of no meaning to me, therefore, I tell well the value of T c I can write as equal to E a by 2 R naught minus I have E a by 2 R naught into I have 1 plus 4 R naught by E a into the value of T ambient to the power half. Now, I want to discuss this further. What happens? I want I still have this under root sign, it is not that easy to solve this and interpret this. Therefore, let us try to find out what will be the value of this under root term over here. Let us see the magnitudes first before we can simplify it. We tell ourselves well let me assume that 4 R naught T ambient, that is T ambient divided by the value of E a, let us say is equal to x, or x is equal to 4 R naught divided by E a into T ambient. Well, we are again telling well E a is a large number, R naught is a small number, therefore, we recognize that x is a small number. If x is a small number, I can expand 1 plus x as a binomial expression for half, and what is it I get? I get 1 plus x if I can write an expression. Well, I think we have to be careful about this particular sign. Have I done it correctly? I have, you had T c squared plus E a by R naught, we have middle number squared minus 4 into the first number, and therefore, this number, this particular expression should have been minus over here, because we are talking of middle number squared minus 4 into the first into the last number. We have minus 4 into the first into the last number, therefore, we have minus sign over here, and therefore, I am looking at the value of 1 minus x to the power half, and we know well 1 plus x I can write as if x is small, to the power half, I can write as equal to 1 plus x by 2, and now I say 1 minus half, therefore, I get minus x squared by 8 plus I have the value of 1. Let me get this expression straight. I can write the value of, for x being small, as 1 plus x to the power half as equal to 1 plus x by 2 minus x squared by 8 minus x cubed by 16, or rather I am interested in x small, therefore, I can as well forget about the higher order term, and I can get the value of 1 minus x to the power half. I substitute this, I get the value as 1 minus x by 2, and x squared then still gives me the negative value. I get minus x squared by 8, and I substitute the value here, and ultimately what is it I get? I get the value of T c as equal to the value E a by 2 r naught into I get 1 minus x, therefore, I get 1 minus 1 plus I get 1 minus the value of 1 minus 1, then I get over here the value minus x by 2, x is equal to 4 r naught by the value of E a into T ambient minus I get the value as 4, that is 16 r naught square by E a square into T ambient square. I square these things and divided by 8, and therefore, I have to just simplify it, and immediately what is it I have written here? 1 minus, I have 1 minus, therefore, I have repeated this twice, therefore, I have 1 minus 1 into this within this particular bracket, and if I simplify this particular expression, what is it I get? Let us just write the expression, and we could discuss it in the next lecture. What is it I get? I get T c as equal to E a by 2 r naught into 1 and 1 gets cancelled. Now, I have minus and minus becomes plus. I have 4 r naught divided by E a into I have T ambient, and mind you, here I should have had x by 2, another 2 over here, and therefore, what is it? I have x by 2 and here I have 8, therefore, 2 and 2 gets over here, plus that means 2 r naught over here, and I have 8 2s are 16, 2 r naught square by E a square into T ambient square, minus and minus becomes plus over here. This is the expression, and let us take out the multiply this by this number. I get T c is equal to T ambient plus I get the value as r naught into T ambient by E a, or rather what is it I get? I get T c minus T ambient divided by T ambient is equal to r naught into T ambient square divided by E a. This is the final expression what I get. In other words, I have been able to get the value of the critical temperature in terms of the ambient temperature and in terms of the activation energy and the value of the universal gas constant, and we get an expression something like this. We now know what is the preheat temperature, and we will continue to discuss this further in the next class. Therefore, to sum up, in today's class we started by again looking at the value of the energy release in a particular volume. We said, well, if the conditions of this initial volume is not at the standard condition, but it is at different condition at different pressure, we know how to calculate the value of heat release. We again looked at the heat release curves that is the rate of heat release curves, and we found well the heat release curve goes, that means if I plot heat release as a function of temperature or as a function of time, well it goes like this, maybe especially for large values of heat release, that means heat release is localized in a small volume, initially it takes off slow. And if I were to look at the initial distribution or for the initial conditions till the maximum value is reached, I tell myself heat release goes exponentially like this. Into this I put the heat loss, that means I go to a system and say a system also loses heat just the same way as it gains heat. I was able to define a stable point, an unstable point, that is an ignition temperature, and an auto ignition temperature, that is a critical condition, and we got the expression for the critical temperature. We will continue to discuss this in the next lecture. Thank you.